Dear student, welcome to my channel. Topic of this video is support vector machine. This is the first video on this topic. In this video, we are going to discuss constraint optimization, introduction to support vector machine, that is SVM, optimal decision boundary, margin and support vectors. Now let us start. Constraint optimization. Constraint optimization is a mathematical technique which is used to find optimal solution to problem subject to certain constraint or limitation. So optimization involves either maximizing or minimizing an objective function while satisfying a set of constraints on the variables. Now we will see the example of constraint optimization. For example, maximizing a profit. So this is our objective function which is of maximized nature, and our constraint are budget, that is subject to budget constraint. Second is minimizing travel time. So travel time is our objective function. Our aim is to minimize while constraints are staying within a speed limits. And the similar examples are optimizing resource allocation with limited supplies. Obtain maximum marks within a 15 days of preparation. Introduction to support vector machine. Support vector machines are formulated as constraint optimization problem. Objective is maximize the margin between separating hyperplane and the closest data points, that is nothing but support vectors. And here constraint is all training point must be correctly classified. This ensures that hyperplane separates the classes without errors. Decision variables are the parameters of the hyperplane, that is nothing but weight and bias. In essence, SVM aims to find hyperplane that not only separate the classes but also maximizes the distance between the closest data points and the hyperplane, providing a robust and generalized model. This constraint optimization problem is typically solved using quadratic programming techniques. A classification technique that has this classification techniques has received a considerable attention in support vector machine. SVM also works very well with the high dimensional data and avoids the curse of dimensionality problem. Another unique aspect of this approach is that it represents decision boundary using a subset of the training examples known as support vectors. Although SVM based classification is extremely slow, but however it is very much accurate, and further testing on the unknown data set is very fast. SVM is less prone to overfitting, that is the biggest advantage of this method. It also facilitates the compact model for classification. Maximum margin hyperplane. For example, training data D T1 to Tn with set of n tuples which belong to the two class either positive or negative, and each tuple is described by two attributes, that is A1 and A2. That means data is of two dimensional, so two columns are there and n number of rows are there. Given data is linearly separable, that is we can find a hyperplane such that all plus point reside on one side of the hyperplane and all minus circle reside on the other side. However, as shown in below figure, there are infinitely many much such hyperplanes can be possible. Although their training errors are zero, but there is no guarantee that hyperplane will perform equally well on previously unseen example. For example, here these are the two classes, two attributes are there, A1 and A2, that is data is two dimensional. Now this is one class and this is another class. Now here n number of hyperplanes can be possible between the two classes. For example, if we keep one as a hyperplane to separate the two classes, then it is very close to plus class. So in future it may happen that even in testing, even one of the sample goes to this side and it will classified as a negative. So this one hyperplane 1 as a biased. Even similarly case for the 2. Then if we see the third hyperplane and fourth hyperplane, they are also biased because they are positive, because they are very close to that margin is not sufficient, and this here we can see that this is very close to the plus point and this is very close to the negative class. So in future it may happen that the misclassification comes because training data, it give the success on the training data, but it will not give the success on the testing data if any one of the data just shifted by some units to this particular boundary. Then if we see the 5 and 6 hyperplane, they are the better one than the previous because they are having the maximum margin between the two classes. So that is the problem, that n number of hyperplanes can be possible, but with quadratic programming we can, or optimizing by using the Lagrange's method, we can find out the best hyperplane between the classes which separating with a proper or maximized margin. Now see, consider the two decision boundaries B1. Now we see B1, that is B11 and B12. So two classes are there, and for example if we use this as a support vectors, that is B11 and B12, and for this H1 is decision boundary. So here we can find out that there is a sufficient between the two classes. So for example B11, this plus becomes a support vector, and for this B12, this particular sample becomes a support vector. So for example, just make assumption that here one sample is present, then this has a sufficient margin between the two classes. Now we will see the another boundary, that is nothing but B2. If we see the B2 and if we see the support vectors for the B2, that is B21 and B22, we can see that the margin is not wide, and at the same time it is very close to the particular classes, that is respective classes. So in future mixed classification can occur. So for this problem the best boundary is nothing but B1, which is supported by the support vectors B11 and B12. So we are now solving for the linear separable problem. So data is linearly separable. We require to find out the decision boundary which will separate the two classes. But when we are drawing the decision boundary, at the same time we require to ensure that two classes are maximum separated by the hyperplane. So these are nothing but the margin. This is the decision boundary. These are the two margins, and which are represented by the particular support vectors from each class. So there may be one or more support vectors are there, or the point which is closest to this boundary can be represented as a support vectors. So in this way our aim is to find out the decision first support vectors. They will form the margin, and in between our decision boundary lies. Now support vector machine problem can be easily extended for the multi-class also. So here multiple classes are there, all classes are linearly separable, and support vector machine draw the boundary between them. Separating hyperplanes for SVM. For example, if our data is one dimensional, then separating hyperplane is a simple point. When our data is two dimensional, our separating hyperplane is a line. When data is three dimensional, our separating hyperplane is plane, and for three or more than 3 dimension we are calling the separating hyperplane as a hyperplane. Now we will start with the one dimensional example. Suppose that we have two classes in one dimensional, class 1 having the points -1, -2, -3, and class 2 having the points 1 to 3. So this data is one dimensional, so it can be represented only simply on the x-axis. So this is 1, 2, 3, that is one class data, -1, -2, -3, this is the second class data. Now when we want to separate out these two, for one dimensional we can easily see that -1 becomes the support vector for this class, and +1 becomes the support vector for this class, and we can easily draw the boundary between the two. So 0 will comes as a boundary. These two classes are linearly separable in one dimensional, and we can find a single point that separates them. Optimal separating point. The goal of SVM is to find a point analogous to hyperplane in higher dimension that maximizes the margin between the two classes. The optimal separating point would lie somewhere between the two classes. The margin would be defined as distance between the closest point on each class that's separating the point. In this case, two classes have their closest point as -1 and +1. So for this example, this is the support vector for this class, and this is the support vector for this class. The optimal separating point would be 0. This point maximizes the margin between the two classes because it is equidistant from the closest points. The closest points are nothing but the support vectors. The support vectors in this case are the points which are closest to the separating point, which are -1 and +1, and these points define the margin. Now we can see, as data is one dimensional, we can simply use the midpoint. So -1 + 1 divided by 2, which is equal to 0. So our midpoint is 0. So decision boundary, that is x equal to 0. So if any sample comes whose value is 0, it will lie on the decision boundary, and our margin is 1 minus -1 is equal to 2. And here we can see that if it is a 2 unit distance, that is a total margin, and this is our decision boundary, that is x equal to 0. So when any sample comes whose value is 0, it will lie on the decision boundary. For simplicity, we can choose w equal to 1, meaning that distance from the decision boundary increases linearly with x. Now the equation of support vector machine contains two parameters. One is the vector w and the bias b. So equation is wx plus b. So here, as data is simple one dimensional, we are choose the w equal to 1, that the distance from the decision boundary increases linearly with x. Now here the bias b is chosen such that decision boundary wx plus b equal to 0 holds at x equal to 0. So because x is our 0 is our decision boundary, so when we take the sample when x equal to 0, the value should come here. So here to adjust this, so when w, here we are keeping w is equal to 1, when x0 comes, then the answer should be equal to 0. That's why we adjusted b equal to 0. So bias is adjusted in such a way that, therefore we are getting the equation like our decision boundary is f of x is equal to wx plus b. So here our w is 1, p is 0, and this is our equation. So when we take any unseen sample x, when f of x is greater than 0, then it is belong to one class, and when f of x is less than 0, then it becomes, or it belongs to the another class, that is nothing but negative class. So here positive and negative class is not fixed, so we have to decide which class is positive and which class is negative. So in conclusion, we have w equal to 1 and b equal to 0. So this is a simple problem with decision boundary at x equal to 0. Now we'll see the another problem. Now here two classes are there, one is 2, 4, 6 and another is -3, -5, -7. Here I have drawn on a line so that you can easily understand. Now the decision boundary lie between the center point of this. So -3 plus 2 divided by 2, that is a midpoint. We are taking simply midpoint because it is one dimensional problem. So here -0.5 will comes as a decision boundary. So this is 1, 2 and this is minus point. So this will comes as our decision boundary. Now our decision boundary, so when we give any unknown sample x, then at that time if it is satisfying the particular condition, so it will gives out whether the point is in this class or on the decision boundary. So here our decision boundary is x is equal to -0.5. Now we require to find out the distance between the two classes, that is nothing but margin. So distance between the two vectors is, this is the supporting vectors for this class and this is the supporting vector for this class. So margin is equal to 2 minus -3 is equal to 5, and you can see that the unit distance 1, 2, 3, 4, 5 is equal to 5. Now we require to choose w and b in such a way that when the particular points comes, then at that time when the point comes at decision boundary, our answer should be -0.5. So the weight w is inversely proportional to the margin. So we will see with this example that here our weight is always inversely proportional to the margin. For simplicity, as data is one dimensional, we can set w equal to 1 and margin is equal to 5. Now this is important, the bias b is determined by the condition that decision boundary at x equal to -0.5. So we have to set in such a way that bias is equal to, because when this point comes on the decision boundary, our answer should be 0. When the point comes on this point, our answer should be greater than 1, and for this our answer should be greater than less than 1. So here we require to make the bias as 0.5. So when -0.5 comes, so w is 1, so -0.5 plus 0.5 equal to 0. So whenever any unseen sample comes which lie on the decision boundary, our answer should be 0. For this class, if we say this class as positive, our answer should be greater than or equal to 1, and if we say this class as negative, our answer should be less than 1. Now our decision function becomes wx plus b. So here w is 1, x that is nothing but any sample which is coming in the future, plus 0.5. So this is x equal to x plus 0.5. So in future when x minus 0.5 comes, because our decision boundary lie on minus 0.5, so when it comes, then our answer becomes 0, because that particular point lie on the decision boundary. When f of x greater than 0 and f of x less than 0, it will belongs to the particular classes, positive and negative class respectively. Now for SVM, when our data sometimes linearly separable, our data sometimes non-linearly separable. So this is the example when data is our linearly separable. So this is the 3 class and data is perfectly linear separable, but it may happen that our data is non-linear separable. So SVM perfectly acts on either linearly separable data or non-linearly separable data, but for that we require to use different types of kernel. So in my subsequent videos I will show you that how we are using the different kernels to deal with the different types of data. So here the data is non-linear, so we require to separate out the data in such a way that, so for example, if we plot the circle, then data gets separated. This is one class data and this is another class data. So here also linear boundary will not work, so we require to make the circle in such a way that this data belongs to the one class and the remaining data belong to the another class. So for that SVM is using the SVM kernel tricks to handle the non-linear data. Now optimal decision boundary. In SVM the goal is to find hyperplane decision boundary that maximizes the margin between the two classes. The margin is the distance between the hyperplane and the closest data points, which are called support vectors. Maximum margin. The decision boundary is placed in such a way that it maximizes the distance between the boundary and the nearest data points from each class. Support vectors. The data points that lie closest to the decision boundary are called support vectors. These points are crucial because they define the margin and the decision boundary. The optimal decision boundary is calculated using the constraint optimization problem, because n number of decision boundary can be present between the two classes. The objective is to maximize the margin subject to the constraint that all training points are correctly classified. This is typically formulated as quadratic programming problem and solved using specialized algorithm. Now how we start with the SVM? Start with all data points. Initially all points are considered potential support vectors. Optimization problem. SVM solve quadratic optimization problem to find the hyperplane that maximizes the margin while correctly classifying the points. Identify support vectors. During optimization, only the points closest to the decision boundary end up influencing its position. This becomes the support vectors. Calculate the hyperplane. The optimal hyperplane is determined by support vectors and is defined by the equation wx plus b equal to 0, where w is the normal vector to the hyperplane and b is the bias term. Equation of the decision boundary. For two-dimensional problem with two classes, the equation of line can be written as wx plus b equal to 0. So when x is in such a way that it lie on the decision boundary, then equation becomes equal to 0. W is the weight vector, so direction is perpendicular to the decision boundary. Here the w vector is of two-dimensional because only 2 points are there. X is the feature vector, b is the bias, controls the position of the boundary relative to the origin. So in previous example you already seen that how bias is adjusted such that when the points comes on the decision boundary, the answer equal to 0 and answer greater than or less than 1 for the respective classes. So this is the example. So this is the decision boundary, which is the equation wtx plus b equal to 0. Here transpose is there because this data is again two dimensional and this vector is also have two values. So when we want to multiply the two vectors, we require to use transpose. So because the answer is a scalar value, so this is the decision boundary. So when x comes on this decision boundary, our answer is 0. For this if we choose this class as positive, then here the answer will come 1, and for the rest of the points answer will come greater than 1. This points answer is -1 and less than -1, and this W is perpendicular to the decision boundary. So this is a decision boundary, and W vectors will present in such a way that it is perpendicular to this decision boundary, and this is nothing but the margin between the classes. That is these are the support vectors which define this margin. This is the support vectors which defines the margin, and this margin we have to maximize, and at the same times our constraint is to classify all the points correctly. Maximizing the margin. The margin is the distance between the decision boundary and the closest points from each class. For each point we want to ensure that distance from the decision boundary satisfied. So this is our equation, yi wxi plus b greater than or equal to 1, where yi is a class label which is +1 for one class and -1 for another class, and the objective is to maximize the margin, which is equivalent to minimize 1/2 norm of the vector w square subject to the above constraint. So this is the equation of hyperplane. This is the equation of support vector machine, and when we are maximizing the margin, at that time we require to minimize this condition, that is 1/2 norm of the vector w square. Support vectors are the points that lie exactly on the margin. They are the closest points to the decision boundary and define the margin width. These points satisfy the equality condition. That is why at wxi plus b equal to 1 for positive class. So when x points is support vector, then for the positive class this condition is satisfied, and when this x is a support vectors for the negative class, this condition is satisfied, and if for remaining points, then the distance is greater than or equal to 1 or less than or equal to 1. Next is solving the optimization problem. To solve the problem, that is to find out the base decision boundary, we require to use Lagrange's multipliers and find the value of w and b that maximizes the margin. Once we have the optimal w and b, the decision boundary is defined and the support vectors are identified. So this is the same diagram, and here whatever this w vector is always perpendicular to this decision boundary. So this is decision boundary, this is a support vector for one class, support vector for another class, and w direction is always perpendicular to the decision boundary. So this margin is given by 2 divided by norm of the w. So we want to maximize this margin. So when we want to maximize the margin, we require to minimize this equation. So when we minimize 1/2 norm of the w square, and when we minimize this, then at that time we are getting the maximum value for this margin. So when with the simple example illustration, you immediately come to know how to calculate all this value. So all this about the introduction of the SVM. Thank you.